In this video, we'll discuss near-number expressions and limits, which is where we'll reconnect with the traditional calculus curriculum, informed by what we've learned about near numbers. Before we do so, here's a logical warm-up question. What is the following shape? If you said it's a square, you're correct. But if you said it's a rectangle, you're correct as well. Your answer is just not as specific. You might have even said parallelogram, quadrilateral, polygon, etc. What we've just seen doesn't constitute any sort of contradiction or logical flaw. It's simply due to the fact that a square is a type of rectangle. Our answer is a description, not an equality. This exact situation is possible when we plug a near number into an expression. For a simple example, take the expression x plus 1 over x, and suppose we want to know what happens with it when x goes to positive infinity. If we plug in directly, we find x plus 1 over x, when x goes to positive infinity, goes to positive infinity plus 1 over positive infinity, which goes to positive infinity over positive infinity, which is one of our star forms. More precisely, the result is the constant interval 0 infinity of all positive real numbers. We have an indeterminate statement because lots of things fit into this target, some of which converge and some of which diverge. But something quite different happens if we simplify the expression first to 1 plus 1 over x, which it equals for any non-zero real number x. 1 plus 1 over x when x goes to positive infinity goes to 1 plus 1 over positive infinity. 1 over positive infinity goes to 0 plus, and 1 plus 0 plus goes to 1 plus, so this has a limit of 1. This might be a bit startling at first glance. Two distinct answers arising from expressions that are equal to one another for any non-zero value of x. But this is what needs to happen if our objects are to fit the way that such computations work. How we write an expression really does need to matter. Our initial discomfort is simply a matter of being too accustomed to the world of equality of static real numbers. Remember that these are arrow relations between near numbers, and each says something logically valid. The first computation says the result fits into star, which it does. The second computation says the result fits into 1 plus, which it also does. Both statements are correct, and they're entirely consistent with one another. The second one is simply more specific, and it tells us enough information to determine a limit. The phenomenon we've just seen can happen with near number computations when we put a near number in for a variable that occurs more than once in an expression. It bears repeating that even though two expressions might be equal, for every individual real number we plug into them, they can still yield different results when a near number is substituted in, and this is not a problem. Algebra is something that we do with expressions before we plug in near numbers. It uses equal signs which work in either direction. Once near numbers are introduced, all we do is compute, one step at a time, using the arrow relation which can have a direction. It's this directionality of the arrow relation that allows us to obtain different results without creating a contradiction. Almost all of the arrows in these computations are actually equivalences, if we replace that last star with the more specific result 0 infinity dot. In our first computation, the only step that is not an equivalence is that first step, when we substituted x goes to positive infinity in for two different x's, which leaves the possibility of a more specific answer. In our second computation, because there's only one x, we have equivalences all the way across. This is the reason that we'll typically not bother with equivalences here, even when we could. Because as soon as we substitute a near number in for more than one occurrence of a variable in an expression, our conclusion is forced into one direction, even if every other step is an equivalence. As we've just seen, near numbers enable us to show every step of such a computation in a rigorous and verifiable manner, whether or not the computation succeeds in giving us a conclusion about the limit. Indeed, the step right before the star shows us where things fell apart. Having all the steps written down allows us to trace that back to our original expression, giving us a hint about what we need to express in a different way. Our simplified form of the expression avoids the division of infinity by infinity, which is why we didn't get an indeterminate statement the second time around. Before we leave this example, there's a completely reasonable question that we should address. Why does it matter that x occurs more than once in this expression? The answer is that once we've substituted that x goes to positive infinity, the fact that those two x's were equal is lost. Anything else that goes to positive infinity could have been there just as easily. For instance, x squared plus 1 over x, when x goes to positive infinity, fits into positive infinity squared plus 1 over positive infinity, which fits into positive infinity plus 1 over positive infinity, which fits into positive infinity over positive infinity and gives us a star. Simplified, this becomes x plus 1 over x as x goes to positive infinity, which fits into positive infinity plus 1 over positive infinity, which fits into positive infinity plus 0 plus, and gives us positive infinity, so this diverges. In another case, x plus 1 over x squared, when x goes to positive infinity, goes to positive infinity plus 1 over positive infinity squared, which gives us again positive infinity over positive infinity, which gives us a star. Dividing the numerator and denominator by x, this becomes 1 plus 1 over x, all over x, when x goes to positive infinity, goes to 1 plus 1 over positive infinity, goes to 1 plus 0 plus over positive infinity, goes to 1 plus over positive infinity, goes to 0 plus, so this has a limit of 0. Before we rewrote these expressions, they all ended up in the same form, but with quite different results when we simplify first. The result that they share before simplification shows us the full range of possibilities for any particular case. In fact, this is exactly what we would get for x plus 1 over y when x and y go to positive infinity, in which case there would be no more specific result possible. X plus 1 over y when x and y go to positive infinity is equivalent to positive infinity plus 1 over positive infinity, which is equivalent to positive infinity over positive infinity, which is equivalent to the constant interval 0 infinity. When substituting near numbers into an expression, star forms are our principal obstacles, as they result in indeterminate statements. Fortunately, there are a few common techniques for getting around star forms. When we see positive infinity over positive infinity, or positive infinity minus positive infinity, we most often factor out the largest terms for the expressions that yield the positive infinities and simplify. If at least one of them can be kept from being positive infinity, the star form will be avoided. When we come across 0 plus minus over 0 plus minus, we generally try to find a common factor from the numerator and denominator to cancel, possibly rationalizing first, to make at least one of the numerator and denominator not squeeze towards 0, so that the star form will be avoided. Also, keep in mind the special trigonometric polynomial relationships. Sine theta over theta, when theta goes to 0 plus minus, goes to 1 minus. And 1 minus cosine theta over theta squared, when theta goes to 0 plus minus, goes to 1/2 minus. Remember that to use these formulae correctly, the expressions on the left must fit those exact forms, and that theta must be squeezing towards 0. The form 0 plus times positive infinity can be turned into a fraction of the form 0 plus over 0 plus, or positive infinity over positive infinity, by reciprocating either factor and moving it to the denominator. Finally, star forms for powers are just hidden star forms for multiplication, as discussed in the previous video. We rewrite them in terms of the natural logarithm and exponential functions. When we need to bring out the big guns, L'Hopital's rule comes out very nicely in terms of near numbers. If either f of alpha and g of alpha both fit into 0 plus minus, or g of alpha fits into positive infinity, and if f prime of x over g prime of x when x goes to alpha fits into L plus minus dot, positive infinity, or negative infinity, then f of x over g of x when x fits into alpha does the same thing. Moving on to limits, let's start by considering the traditional limit statement that limit x goes to a f of x equals L. In this notation, there's an implicit plus minus on the a, and when we say that the limit equals L, we really mean the values of f squeeze closer and closer to L. We can state this much more concisely and precisely via near numbers. F of a plus minus fits into L plus minus dot. The limit asks for the number to which f of a plus minus is squeezing, if such a number exists. Limit notation, in addition to using an equal sign when nothing involved actually needs to equal L, and the problem that limits don't always exist, has a more substantial flaw. It forces all of the logic of this statement into a single rather cumbersome definition. In contrast, the statement that f of a plus minus fits into L plus minus dot works in a much more structured fashion. The near number a plus minus has a very specific meaning in and of itself. The function f transforms this input, resulting in another near number, and that result fits into all the targets painted by L plus minus dot, which again means something in and of itself. Each of these elements, the near numbers, the arrow relation, and the operation of the function, can be studied independently, providing scaffolding that helps to build a more complete understanding of exactly what this all means. In fact, every limit statement for a single variable function, as well as many statements that can't be accurately expressed via limits, can be expressed in the form f of alpha fits into beta for some near numbers alpha and beta, and they all follow exactly the same logic. For example, limit x goes to a from the right f of x equals L is expressed as f of a plus fits into L plus minus dot. If we have cause to, we can even make more refined statements, such as f of a plus fits into L minus, which is not possible using limits alone. Limit x goes to positive infinity f of x equals L is expressed as f of positive infinity fits into L plus minus dot. Limit x goes to a plus minus f of x equals positive infinity, abusing both the equal sign and the notion of limit, is expressed correctly as f of a plus minus fits into positive infinity in exactly the same way as the rest. Limits are not about static real numbers, and they never have been. Near numbers simply give us the language to say what we've actually meant all along, rather than trying to talk around it. Let's look at an explicit example of a failure of limit notation. Consider the following two limits. Limit x goes to 0 from the right of x, and limit x goes to 0 from the left of x, both of which equal 0. If we reciprocate x, the corresponding limits do not exist. If we then apply the arctangent function, now the limits exist again, but they have different values. Limit x goes to 0 from the right of arctan of 1 over x is pi over 2, while limit x goes to 0 from the left of arctan of 1 over x is negative pi over 2. We began with expressions having identical limits. Reciprocating gave us limits that do not exist, and applying the arctangent gives us expressions whose limits exist again but are not equal. We could even skip the middle step, moving from two identical limits to two different limits via application of a function. This runs counter to everything that we expect about functions, and it's a serious indication that we're not stating this as best possible. All of these statements we've tried to shoehorn into limit notation are expressed much more clearly and consistently via near numbers. 0 plus and 0 minus are objects in their own right. We can reciprocate them. 1 over 0 plus goes to positive infinity, and 1 over 0 minus goes to negative infinity. In fact, these relationships are symmetric. 1 over positive infinity goes to 0 plus, and 1 over negative infinity goes to 0 minus. Then we can apply the arctangent function. Arctangent of 1 over 0 plus fits into arctangent of positive infinity, fits into pi over 2 minus. And arctangent of 1 over 0 minus fits into arctangent of negative infinity, fits into negative pi over 2 plus. Equipped with the right objects, these computations are straightforward, working inside out as we'd like them to, and the finite and the infinite work seamlessly alongside one another. Now let's talk about the process of computing limits via near numbers. All that we need to do is literally plug in a near number for the variable and simplify. If the result fits into L plus minus dot for some real number L, then the limit is L. If the result fits into positive negative infinity, then the limit does not exist in a specific way. If we obtain an indeterminate statement due to a star form, we need to restructure our expression or apply some other technique to resolve the indeterminacy. Let's finish by working through one example in its entirety. Limit x goes to positive infinity, x squared plus sine of x over 2x squared minus x. Tells us to compute x squared plus sine of x over 2x squared minus x when x goes to positive infinity. To do so directly, we simply plug in positive infinity for x and work one operation at a time. Positive infinity squared plus sine of positive infinity over 2 times positive infinity squared minus positive infinity. Well, the positive infinity squared yields positive infinity. Sine of positive infinity yields the closed interval negative 1, 1. And again, positive infinity squared yields positive infinity. In the numerator, positive infinity plus the closed interval negative 1, 1 yields positive infinity. In the denominator, 2 times positive infinity yields positive infinity. And finally, we obtain a numerator of positive infinity and a denominator of positive infinity minus positive infinity, which yields star. Our end result is star. Rats, this is indeterminate. Well, we see a star in the denominator, so we should factor out the largest term. While we're at it, let's do the same for the numerator. X squared plus sine of x over 2x squared minus x, factoring out the x squared and canceling it, gives us 1 plus sine of x over x squared over 2 minus 1 over x, as long as x is not equal to 0. Starting over, 1 plus sine of x over x squared over 2 minus 1 over x when x goes to positive infinity fits into 1 plus sine of positive infinity over positive infinity squared over 2 minus 1 over positive infinity. Again, the sine of positive infinity gives us the closed interval negative 1, 1. Positive infinity squared gives us positive infinity, and 1 over positive infinity gives us 0 plus. In our numerator, the constant interval negative 1, 1 dot over positive infinity fits into 0 plus minus dot. And 2 minus 0 plus fits into 2 minus. Our numerator, 1 plus 0 plus minus dot, fits into 1 plus minus dot. And the resulting fraction fits into 1/2 plus minus dot. This has a limit of 1/2, giving us our answer. In both of these computations, every step is rigorous and able to be checked. We leave the realm of static real numbers, which must be done if we're computing limits correctly. But we don't enter some nebulous realm, just that of near numbers, which are explicitly defined and behave according to specific rigorous rules. A few parting words. Near numbers don't change the results of calculus one bit. Limits that existed before still exist and have the same value, and limits that didn't exist before still don't exist. All of the final logical definitions come out identically. But instead of getting there via the classical outdated calculus pedagogy, which woefully undertreats what happens between the expression and the end limit, which is where everything interesting happens, we're able to express exactly what's going on in between. Near numbers flip on the light switch when we want to explore concepts such as convergence, divergence, infinity, indeterminacy, etc., that can otherwise seem fuzzy or confusing when first encountered. With that, we end our introduction to expressions and limits. Our next video will introduce the basic elements of formal definition and proof for near number statements. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.